Okay, so recording started. So good afternoon, everybody. Just as a reminder, you have your next homework posted. So if you look in the classroom under homeworks, here's homework number 3. Has anybody started homework number 3 yet? Just out of curiosity.
Yes, but I was a little confused on one of the questions.
Yeah. Okay. How about this? So just let me just do one quick thing, and then I'll take homework questions. Yep, I'll answer all that in 1 second. Okay. So here's what we're going to do, and then I'll answer your question in a second, Caleb. So today what I'll do is I'll start with homework questions. And then I'll move into probability, or finish probability today, which is a good thing, right? Yay. Finish probability. And then what I'm going to do is we're going to start counting methods. Okay. I don't know how far we'll get in counting methods, but whatever we don't finish in these counting methods, we'll finish on Thursday. Okay, so your homework is posted here. It is due the 16th, so Tuesday the 16th. So 2 weeks from now, we're going to have our next exam, and this homework is designed to help you study for the exam. That's really what the purpose of the homework is. So if you look at the homework, it's a pretty lengthy homework. I forget, it was 8 or 9 questions, something like that. 11 questions, sorry. But these are all just old exam questions, excuse me. So these are the exact type of questions that I would ask on an exam. Okay. So doing this is a great way to study for that exam. All right, so what questions? Is there any problems that people want to see me do or have trouble with on the homework so far? Feel free to ask. Go on ahead. You can ask. You can turn your mic on and ask. Okay, so first up, Marissa, question 1. Question 1 is, do you remember the problem we did that has where I said you flip a coin 3 times in a row? Yeah, it's just all it is now it's doing 4 times in a row. So like look back at like how we did the sample space with the tree diagram. It's going to be a big tree diagram. I don't want the number. I want the actual sample space. So the first flip you're going to get is a head or a tail. And then the second flip, you're going to get another head or a tail. And you're going to have to do this 4 times out. Yeah, there should be 16 things in the sample space. Yes. And then once you get this, you'll be able to, I'll put this tree diagram, up in the notes, so you guys can see. But then you'll just have to traverse the tree diagram and find what the sample space is. It's a little bit of a pain. I wish I'd taken a little bit more space for this now, but you get the idea. So like the first one in the sample space is head, 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 and the last one is tail, 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 tail. Okay. And then from there, you can answer the probability questions. So for question 1, I think Marissa asked that. Does that help? Help you get started on that? Okay, great. And then what was the next question that seemed a little bit tricky? People have trouble with question 3? Is that what the next question? All right, so question 3, I'll help you get started on the first one here, okay? So it says, the probability that a randomly selected 40-year-old male will live to be 41 is 0.997. Okay, and this is according to the National Vital Statistics Report, volume 48. So what is the probability that 2 randomly selected 40-year-old males will live to be 41? So basically what was going on here, it says the probability that they live is 0.997. No, I don't think you need the complement rule for this problem. Maybe for the last part you will, Melissa, yeah. But for the first one here, what is the probability that 2 win, or 2 live? So it's the probability the first lives and the second one needs us to live. Okay. When you see the and statement, what does that imply? This we learned last class. Multiply, 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 multiply. So before you multiply, you have to ask yourselves, are these independent, right? So like, I'll be 40 next year. If the probability I live or die, do you think that is going to impact the probability that some other random 40-year-old person in the entire country is going to live or die? Yeah, so they're independent. Yep. So it's just the probability the first person lives times the probability the second person lives. Well, the probability that they live is 0.997. So it's 0.997 squared. So that's how you tackle that problem. And then when you get to this last one here, whenever you see an at least, whenever you see the words at least, that tells you it's going to be a complement rule, most likely. Okay. All right. Did that help get number 3 going? Yay, nay. Okay, thanks. Thanks. Okay, good, good, good. Any other questions? So after today's class, just before I take any other questions, after today's class, you'll be able to do number 5, number 6, definitely 5 and 6. And then the rest of them are counting type problems and binomial problems. We'll probably get to a lot of that on Thursday. Whenever you see the words at least, you see what I'm highlighting on the sheet there? At least one, at least one, at least one. That whenever you see that, that's going to be your hint to use the complement rule. Okay. Yeah, no problem. Okay. Any other final questions before I start today's lecture? All right, I will just say this, okay? This probability is for whatever reason, I wish I knew why, okay? But for as long as I've been teaching this class, the probability stuff, it tends to be the section that gives students the most trouble. Just because it's a little abstract and there's no like clear-cut formula to follow like every single time. So I'm, I always try to be honest and straight shooter with you guys. Like everybody, there's 4 exams and I drop your lowest exam score, so if you really struggle with this and you bomb the next test, and I'm not saying that'll happen, but if it does, you like, don't worry, don't stress out. Like, we're just going to move on. And, I think that the next section gets a little bit easier, honestly. Okay. That being said, I still think the probability stuff is fun, but that's just me. All right. So what no, so no exam is cumulative. So no. Yeah. And I'll post a practice exam for you guys next week too. Okay. I'll try to get it done by Thursday for you. You know what? I'll even put it on my to-do list for tomorrow so that it'll be up for class on Thursday. Okay. I'll give you a chance to get some more practice in. All right. So what I want to do today for probability is we have two more rules. Okay. We have something called conditional probability, and then we're going to have something called the general multiplication rule for dependent events. Okay. So conditional probability, just kind of like an introduction to it. It's when you compute a probability but you're given some extra information. Okay. Like, let me ask you this. Okay. Suppose, and I'm going to set this up with an example. Okay. Suppose you take a 6-sided die. Okay. And you roll it, and, as soon as it lands on the floor, I cover it up so you don't see what you got. Okay. What's the probability you just rolled a 5 on a 6-sided die? Don't overthink this. Okay. Like, if you just roll a 6-sided die, what's the probability the number 5 comes up? Yep. Just 1 out of 6, right? That's it. Perfect. Thank you. Now suppose, okay, remember you rolled the die, and as soon as it hit the ground, I covered it up so you don't see what your result is. If I look at the die and I say, hey, guess what? You just rolled an odd number. So I'm giving you an extra piece of information. Okay. Now, what is the probability that you rolled a 5? Given, so I'm telling you, given you rolled odd. Close. No, it's not 3 out of 6. You guys are close. I understand. I understand what you guys are just told me in the chat. There was where your mind was going, is that it's there's 3 odd numbers. Brianna, why is the answer 1/3? That's the correct answer. Yeah, there are 3 odd numbers. Okay. So the 3, I'm telling you, rolled an odd number. So you either rolled the numbers 1, 3, or 5. Okay. So the probability you rolled a 5 then, okay, well, there's 1 5 on the die, but there's 3 odd numbers. Okay. So do you notice how, like, when I give you an extra piece of information here, under the rule, it says when you compute a probability, but given extra information. So you're given extra information. Yep. So do you notice here, like when I told you it was an odd number, the probability changed? Like it was no longer 1/6, it changed. Everybody sees that? So that's what conditional probability is going to be. I'm going to ask you to compute a probability like rolling a 5, but I'm going to give you some extra piece of information. All right, so let me give you the formula for it. The probability of event F occurring given, okay, given, so notice how I have this given here, given that event E has also occurred, is given by. So we write it as this. It's the probability of event F given event E. So whenever you see this vertical line inside a probability statement, it means the information is given. Okay, so I want to find the probability of event F, and you're told, hey, wait a second, event E just happened. Okay. It's actually a pretty simple formula. There's 2 ways you could do it. You could do it as the probability that event E and F happened, and you would just divide that then by the probability of event E. And I'm going to show you that this formula works by working this problem, okay? Or another way you can do it is it's the number of ways events E and F can occur. So it's the number of ways events E and F can occur together, okay, divided by the number of ways E can occur. Okay. All right. So let's compute this very, very simple problem again, but use the formula, like just to make sure that it can happen. Okay. And is everybody okay if I go to the next slide? Okay. Sorry, I think I let out a yawn there. I don't know if you guys heard that. Okay. Yeah. So here's the problem. Okay. So I want to work this problem again and just show that this formula works. And I'm going to use all this notation for you. Okay. So if you roll a 6-sided die, what's the probability you roll a 5 given you rolled an odd number? Okay, what's probably you rolled a 5 given, so you rolled a 5 given you rolled an odd number. So you'd write it as this: probability roll 5 given you rolled odd. Okay, so this is that formula, probability of event F given event E just occurred. So my event F is rolling a 5, and my event E is I rolled odd. Okay. So this is the probability that event E and F occur divided by the probability that event E occurs. So what we have to do is we have to rewrite this in this notation here. All right, so it's the probability you roll an odd number and you roll a 5. Divided by the probability of E. Remember, E is probability rolled odd. Okay, so don't overthink this. Okay, don't overthink this. If you roll a 6-sided die, what is the probability that the number you rolled is both an odd number and a 5? You're gonna roll a 6-sided die. What's the probability that it comes up as an odd number and a 5? That's it. It's exactly, it's 1/6. The only way you can, it's 1/6. The only way you can roll a 6-sided die and have it be both an odd number and a 5 is that you roll the number 5, because that is both an odd number and the number 5. So there's one way to do it out of 6 divided by, and now what's the probability you rolled an odd number on a 6-sided die? How many odds are there? 3 out of, I got you, 3 out of 6. Okay. So now look here, you have a fraction. So, because it's just odd, I'm only asking you right here, what's the probability you rolled an odd number? Odd. Okay. So the top is an odd number and a 5. So if you look at the sample space for a 6-sided die roll, it's just these 6 numbers, right? And the only way you can roll an odd number and a 5 is that you roll the number 5, because the numbers like 1 and 3 are not both odd and a 5. They're odd, but they're not the number 5. So that's why the top is 1/6. The numerator is 1/6. So here you have a fraction divided by a fraction. So have you guys heard of the keep, change, flip method for solving these things? Keep, change, flip.
Yes.
Yeah. So what you do is you keep the top fraction, you change division to multiplication, and you flip. So 3/6 becomes 6/3. Then you multiply across. So 1 times 6 is 6. 6 times 3 is 18. Would you look at that? It simplifies to 1/3, which is exactly what we said we would get. Okay, so this formula works. Okay. All right. Coin flip die rolls, not the most interesting, right? You know, I understand. So let's do a, I have a more interesting example to show how I'll ask you conditional probability on your exam and how it comes up on your homework. So is everybody okay if I go to the next slide? Got one yet. All right. All right, so this is going to be, this was example 1. I'm going to just have this one big example here. And this example is going to be about computing probabilities from a table of data. So what I mean by table of data is if you look at your homework, you'll notice in question 5, I have this like table of data here. It has, a column and row headers, and then it has some numbers in it. So what I have here, I'm not making this data up here, okay? What I have here is I have passenger data. On the Titanic voyage. A little bit of a macabre example, I'm sorry. Okay. Everybody know of the Titanic? We've all heard of this?
Yeah.
Yeah. It was immortalized in a movie starring what 2 people?
A lot of conspiracy theories behind it too.
The Titanic? I don't know. Now I'm going to, as soon as class gets over, I'm going to Google conspiracy theories and Titanic. But yeah, it was a movie with Leonardo DiCaprio and Kate Hudson, right? I have gone down on too many YouTube rabbit holes. Tonight probably would be a bad idea. So what I have here, let me give you the data. Okay, so what I have here is I have data on
PTSD.
it's
from the child.
I'm going to mute everyone's mic but mine here for a second. So what I have here is I have data on the number of passengers who survived and who died in the Titanic. And then I have it broken down if they were male, female, or just a child. So a child, they don't break it down by their sex, if they were male or female, okay? All right, so the number of people who survived the Titanic. There were 338 males who survived the Titanic, and there were 316 females who survived the Titanic, and there were 57 children who survived the Titanic. Okay. Let me give you the macabre numbers here, the morbid numbers. So unfortunately, there were 52 children who died on the Titanic. There were, yes, this is real info, Jamie. I'm not making this up. Okay, there were 109 people or 109 females who died on the Titanic. And then there were 1,352 males who died on the Titanic. Okay. Yeah, oof is right. So, if you think about it, oh gosh, I should have prepped this ahead of time. I think the Titanic was 1916.
Yes, it was.
Yeah, thank you. So just a different time. Okay. So just a different time in America. And a lot of these people it looked like were probably people who worked on the boat. Okay. So here's what you're going to do. Imagine you have a list of passenger data. Okay. You have a list of everybody's name. Okay. And all their information. If you select a passenger at random, and so on the next page, I'm going to ask you a bunch of questions. Okay, I'm going to ask you a bunch of probability questions. But when you're given a table of data like this, what do you think might be the first thing you're going to want to do with these numbers? Yeah, you want to add them all. Yeah, you want to add, here's what you want to get. You want to get row sums and you want to get column sums, okay? So I have these numbers just to save some time, but the number of people who survived the Titanic, if you add this number, and this number, there were 711 people who survived the Titanic. And if you add this number and this number and this number, there were 1,513 people who died on the Titanic. The number of male passengers on the Titanic was 1,690. The number of female passengers on the Titanic were 425. And the number of children on the Titanic, there were 109 children. So the total number of passengers, you can add this number and this number, or you could add these three numbers. And it looked like there were 2,224 total passengers on the Titanic. Okay. All right. Is everybody, I'm going to keep coming back to this slide, but does everybody have the information down who wanted to copy it down?
Yes, thank you.
Okay, good. Okay, so what you're going to do, imagine you have everybody's name in a hat, okay, basically. And what you're going to do is you're going to shuffle it up and you're going to pull one passenger name out of the hat, okay? So the first question I have for you is, what's the probability they survived? Okay, so it's the probability that this person survived the Titanic. So here's how you're going to tackle this. Okay, I'm just going to write this one out so you can just exactly see how this is solved. Okay, whenever you have this is just one person. Okay, so it's going to be a very simple division problem. It's going to be the number of people who survived divided by what? What are you going to divide this by?
The total?
Yeah, the total number of passengers. Yep, and Jamie has the answer in the chat there. So if you just look back here, it looked like there were 711 people who survived, and there were 2,224. So let's grab our trusty calculator. And it looks like when I rounded it, like 32%. Okay, so it's 0.32. Okay, so another way to interpret this, just so we're clear what this means, is 32% of people survive. Not bad. Actually, that's terrible. What am I talking about? Okay, should have been more. All right. Nothing new. Yeah, that was pretty bad. I can't believe I said not bad. Worst part is this is recording, and then we'll live on YouTube forever. So I will be judged harshly. Yeah. Thank God I don't get any views on my YouTube page. So
I'd be more worried about the dad jokes.
more worried about the dad jokes. Yeah. Yeah. Okay. So now let me throw something at you here that's a little different. Okay. And it goes like this. If a child was selected, what's the probability they survived? All right, so this one's a little different, right? So listen to this. What am I telling you, or what am I telling you was selected? What type of a person was selected? A child. Okay, so listen to this. Listen to this. I'm telling you that a child is selected. So I'm giving you, you're given that a child was selected. Okay. This is a roundabout way of saying given a child was selected. So if you look back here, this is going to be a conditional probability question. All right. So it's the probability. I'm looking for the probability they survived, given that they were a child. So if you look, this is the way we're going to tackle this formula. It's the number of ways both can happen. In that case, it would be the number of children who survived divided by whatever the thing is behind it. So the thing that's in the you guys can all see my mouse, right? In this case, it would be the number of total children. So it would just be the number of children and survived divided by the total number, in this case, of children. Well, for anybody who copied the data down, how many children survived?
57.
Yeah, how many total children were on there? Yeah. So it looks like the probability that a child survived, it was, if you take this and plug this in your calculator, you'll get 0.52, around 0.52. So, you know, it is what it is. It's also very sad. So you see the subtle difference to how that was worded compared to the first one? Hopefully. Okay. I got two more questions for this to ask you. All right, so everybody okay if I go to the next slide? Okay, so third question here. So if a woman was selected, what's the probability she survived? So here you're given that what type of, person was selected. Were you given that man, child? You're told that a woman or a female was selected here. So you want to find the probability they survived, given that the person was a female. So this is just the number of passengers that were female and survived. Female and survived. And I divide by the total number of what? Yep, total number of women or females. So let's look back. Okay, how many females survived the Titanic? Is it 316? And then how many total women were on the Titanic? Yep. So it looks like this would just be 316 divided by 425. I think that rounds out to be roughly 0.74. Okay, all right, better, right? So like 32% of people survived the Titanic, 52% of children were getting a little bit better, but 74% of women survived the Titanic. That's not bad. I don't know why I keep saying that's not bad. That's still terrible. Should be 100%, but. Okay, final question. If a man or male was selected, what's the probability he survived? So again, I want to find the probability the person survived given they were a what? Yep, given that they were a male or man. So again, it's just the number of passengers who were male and survived divided by the total number of male passengers. Yep, and that's right in the chat there. So if you look back here, right, there were 338 males who survived. There were 1,690 total males. And so that, I think if you were to plug that in your calculator, it would be roughly 20% or 0.20. So this is why Leo didn't make it and why Kate did. Okay. That's my bad joke for the day.
No, that was actually a good one.
That was a good one? Oh, thank you. Thank you. I tell that every semester. Melissa had a fantastic one in there too. That wins the day. Okay. So you'll be able, this is how I'll ask or handle conditional probability on the exam and on your homework. I don't want to spend too much time on conditional probability. What's really important is the notation for it. Okay. Because it's going to help us set up the next and our final probability formula. Okay. Is everybody okay if I go on to the next couple slides? Okay, got one, yep. Okay. And this is it, rule 5, our last rule for probability, okay? And this is called the general multiplication rule for dependent events, okay? So what exactly are dependent events? So we know independent events, what they mean is the occurrence of the first event does not affect the occurrence of the second. So what do you think dependent events are then? Yeah. So what's going to happen is two events are dependent if the occurrence of the first event affects the occurrence of the second event. Okay. So the occurrence of the first event affects the occurrence of the second event. So basically what's going on here is whatever happens first, it's going to change the probability of what happens second, okay? So our formula for the general multiplication rule for dependent events is going to be slightly different than it was for the general multiplication rule that we saw before. And it goes like this. For any two dependent events, okay, we'll call those events E and F, we have the following. If I ever ask you the probability that event E and event F happen, okay? So again, whenever you write the and statement, what mathematical operator are you going to think of when you see the and statement?
Multiplication.
You're going to see multiplication. So it just goes like this. It's going to start the same. You take the probability of the first event. And now you're going to multiply it by, but here's the thing. When you go to find the probability of the second event F, remember what happens first is going to affect the probability that the second one happens. So you're going to need to multiply this by the probability event F happens given that event E happened first. Okay. So the formulas look it looks a little complicated, but what I want to do in class is I want to show you a way to do this where you tackle it with intuition instead of like getting bogged down in formulas. Because sometimes I think with probability, when you get like bogged down in the formulas, it's a little complicated. Okay. So I just want to do one example. I'm sorry. I should have, my apologies. I didn't say this when I started class. I just got a private message about slides. I actually added these slides on here. I didn't throw them in the PowerPoint. You'll notice that the slides I added are all blank. They're just, they just help me keep track to know what I need to cover in class today. I'm sorry, but there were no slides for this posted in the classroom. I'm sorry, it just slipped my mind. Hope that's okay. The person who, I don't want to say their name because they messaged me directly. So I hope that's okay. My apologies on that. You guys ever have those days where your son wakes you up at 4:30 in the morning and then you forget everything? Kind of messes with your whole day. No laughs. Now I sound like Ted Cruz blaming my son for this. That's terrible. No, I just forgot. I'm sorry. Okay. Oh yeah, I'm sorry. I shouldn't have said that joke. That was a bad joke. This guy actually was kind of a funny joke. Anyways. Everybody ready if I go do one example and then we'll take our break and then we'll come back and we'll do some harder one. All right. So here's this problem, okay? And there's a great way to introduce this, okay? And it's suppose you have a bag of marbles, okay? And inside the bag of marbles is you have 7 green marbles and 3 blue marbles. Okay. So how many total marbles do you have in the bag? Yeah, you have 10 total marbles in the bag. Okay, so imagine that you mix up the bag. So if you select two marbles, one at a time, without replacing the first marble. Okay, so you're not going to put back the first marble. Okay, what's the probability both are green? Okay, that's the question. So here's the deal when you tackle this. When you go to solve these harder problems, and I know you guys have heard me say this before, but like how you write it really dictates how you're going to tackle the problem. So I want two marbles to be green. So I want the first marble to be green and what? So the first marble to be green and the second marble will be what?
Green.
Yep. So the probability that both are green will be written as the probability the first marble is green and the second marble is green. Okay, but now here's the thing. So you see Julia has it right there, but I'm going to walk you through it, okay? When you see this type of problem, the and statement tells me multiplication. So you just have to ask yourself, are these independent or dependent events? Okay. So when you're not replacing the first marble, okay, if you get a green on the first marble, will it change the probability you get a green on the second marble? Yes, absolutely it will. Like if you get green first, there's going to be one less green marble in there to select when you go to get another one. So these are dependent events. So we're going to use this formula here. So it's the probability of the first event, E. So it's probability the first is green times, now when I go to do the probability the second one is green, I have to do given that the first one was green. So it's the probability the second is green given the first is green. Okay. So we have it right in the chat there, but how many green marbles are there in there initially? There's 7 green, and Julia has how many total? Yep. So the probability that you get a green on your first marble is 7 out of 10. Now I'm going to need to multiply. I don't want to get bogged down in this, okay? If the first one is green, I'm going to take it and I'm going to put it off to the side. Okay, how many green marbles are there left to now select? The first one was, yep, there's only 6 left. But now how many total marbles are left in the bag too? Yeah, there's only 9 because you took one green one out. So not only do you knock down a green number, but you knock down a total number. Ah, we got it. So I believe this would be 42 over 90 when you multiply. So you would go 42 divided by 90, and you get roughly 0.47 when you round it. See, it's just generally these type of problems will be like these bag of marble questions, or I'm going to do a different one that seems a little different. The next the next example we come back from break, but it's generally when you're given these small number of things and asked to select 2 of them. Okay. So I want to take our break now. Any questions before we head to break?
Professor, since we're going on break, can you just go back to the other slide and then I'll just copy it during break?
This one right here?
No, the very first one.
This?
The general multiplication rule number 5, the very first one that you did.
This?
Yeah, I believe that's, yep. Thank you.
All right, so let's do break until 2 p.m. All right, so I'll be back in 8 minutes. Everybody enjoy your break, and then we'll pick up with this. We'll do some more examples, and then we'll be able to start counting. Yeah. After this slide, can I copy last slide we did? Yeah. Did you originally ask, Alexandra? Or is that somebody different who asked me to go to this slide?
I'm just gonna take the picture of it and then she can
Okay. So let me know when I can go to the next slide.
okay. All right, you can go to the next one.
Yeah, and don't forget, I'm also going to post these too right after class. So don't stress so much, like it'll be posted after class too. All right, I'll be right back. Okay. Everybody hear me okay? All right, good. So what I want to do is I want to finish up this afternoon. So I want to do one more example of this, and then I want to start counting methods. We won't finish counting methods. We'll get a bunch of it done, and then we'll finish up counting methods on Thursday. Okay. Let's do this example. All right. This is an example about quality control. Are there any gamers, in class? Anybody a big gamer? Yeah. Does anybody play I guess there's a new, is there a new PlayStation and Xbox coming out? Did it already come out?
Yeah, it came out already.
Yeah. Okay. My head's been in the sand for a while. I haven't, didn't know that, but I only bring it up because somebody mentioned it to me the other day. But so imagine that my favorite store, GameStop, gets a shipment of PlayStation 5s. So suppose GameStop, you guys have all heard of GameStop, right? Okay, good. Suppose GameStop gets a shipment of 20 PlayStation 5s. So 20 PlayStation 5s, okay? And they don't know this, okay? But imagine that 16 are working. 16 are working correctly, and 4 are not. Okay, so they don't know this ahead of time. But 16 of these PlayStation 5s work perfectly, and 4 of them are not working at all. Like if you plug them in, they don't work, or there's some software glitches, whatever, okay? And so imagine that they want to test their shipment, right, to make sure that their shipment is okay. All right, what they probably don't do in quality control is they don't test every single one of these PlayStations. What they'll probably do is they'll take a couple of them, maybe 2, and plug them in and just see if they work, okay? So suppose the quality control associate, I'm going to put, the quality control associate randomly selects 2 PlayStation 5s, okay, 2 PS5s. I know my 5s and S's look the same, but 2 PlayStation 5s to test to see if they work properly or they work correctly. Okay. So basically this is what's going to happen. Okay. The quality control associate's going to take one PlayStation 5, plug it in, see if it works. That person will either be like, yay, or no, it's not working. And then go grab another PlayStation 5, plug it in and see if it works. Okay. So I've got 3 questions for you from this. Okay. Does everybody have the relevant information on this slide written down before I go on? I got 1 yes. Okay. So again, just on the next slide here. Okay, we have 20 PlayStation 5, 16 work, and 4 do not work. Okay, and you're going to randomly select 2. First question is this. What's the probability both are working correctly? right, so it's the probability both are correct. Both work correctly. So using the methods we've talked about in class, how would you guys write this? How would you write this so that we could solve it? Anybody got a suggestion? You can turn your mic on too if you want. Or not. I can just drink coffee. What does the first one need to do? If I want them both to work correctly. The first needs to work, and what does the second one need to do?
They
Yep.
both have.
Yeah, so it's probably the first works. And the second works. So now you just have to ask yourself this: are they independent or dependent events? Like if I select a working one first, will it change the probability I get another working one?
No.
Well, so if I take a working one out of the 16,
Oh yeah.
yeah, it's going to change. Yeah, they're dependent events. Yeah. So when you go to tackle this, the probability of the first works times, now when you go to do the probability of the second works, you need to assume or that you're given that the first worked. Okay. What's the probability that the first PlayStation 5 works? So how many working ones are there?
16,
And how many total PlayStation 5s are there?
20.
Now, when you go to select the second one, okay, if the first one worked, how many working PlayStations are left to select? Yep. And then how many total PlayStations are left now?
19.
Yeah. And that's it. So this would be 16 times 15, which would be 240. I believe 20 times 19 is 380. Yeah. So it's 240 out of 380, or the probability that both would work. Yeah, it's a little bit more than 63%. Not too bad. Now that you're seeing me do two examples, you feel like this is something you could recognize? I have no idea how much even a PlayStation 5 costs. I couldn't even tell you. $400 or $500, $300. I have no idea. Does anybody know?
They're like $800. They're expensive,
What? Who has that type
Yeah.
of money?
especially the new one that just came out, the PS5. It was so expensive.
Oh my God. I'm gainfully employed and I wouldn't even do that. That's crazy. I mean, gosh, if I bought enough of them, I guess I could have retired. Shame on me for not thinking about that. Yeah, 300-400 sounds more reasonable. Okay, I've got two follow-up, enough, a little bit of sidebar here, but I got two more follow-up questions for this, okay? So I'm going to go to the next slide if everybody's okay. So remember, you're going to select two. What's the probability both do not work? So that means you're going to select, oh, shoot, I'm on accounting methods. Yeah, sorry about that. Just wanted, my slides were messed up a little bit. But yeah, Melissa has it in chat. So what's the probability that both do not work? So probability, both do not work. You just, so it just comes down to writing it, right? So it's a probability the first does not work. And the second does not work. So do you guys find that when I write sometimes this formula, this second step, it can get a little confusing? Like, is it easier when I go here to just skip to this third step here? I'm curious. Melissa thinks so. Does anybody else think so? Maybe, maybe not. So generally, you know, if I skip a step, like if I don't rewrite this second part here and just go from here to here and do it intuitively, sometimes I think like, yeah, sometimes it can be a little bit easier. Yeah. All right, so we see this and statement. All right, so what's probably the first one does not work? Okay, so how many PlayStations did I say were not working? Yeah, and there were 20 total. Now when I go to the second one, okay, if the first one wasn't working, how many working ones are left? And how many total ones are left? Yeah. So this just becomes 4 times 3 is 12. 20 times 19 is 380. Excuse me. It's only like 3%. Real small. Very, very small probability. Okay. Last question here. And I'm going to tell you this. This problem is tricky. Okay. It's actually trickier than it seems. And for as long as I've been teaching, very rarely do people get this right on the first one. So just pause and think about this. Okay. Remember, you're going to select 2 at random. What's the probability? Remember, just going to select 2. One works and one does not work. So what is the probability that one works and one does not work? I'm going to give everybody, I hope you're paying attention. Please, please just take 2 minutes and try this on your own. Okay, so remember there's 20 PlayStation 5s, 16 work, 4 do not work. Okay, hold on. I'm going to take 2 minutes. Actually, I'm just going to give you 1 minute. All right, just take 1 minute on your own. Okay. And see if you can solve this problem. And I'm going to tell you this. The most common answer is what's the 2 that are written in the chat there. And I appreciate Jamie and Melissa sharing. But that is not the correct answer. Okay, I'll give you a hint. You have some of it right. That's why I said this problem's a little bit harder than it looks. A little bit harder than it looks. I'm going to be quiet for 60 seconds. Give it a shot. All right, I'm gonna stop, okay, and help you on this one. And as soon as you see me explain what the issue is, everyone, at least people who are trying it in chat are gonna be like, oh yeah, I get it. Okay. So now here's the thing. I say you're gonna select two at random, and all I want to find is the probability that one of them works and one of them does not work, right? So my question for you is this. How can you do that? Did I say you have to be very, very careful to the wording here? Did I say I want to find the probability the first works and the second one does not work? Or did I just say I want one works and one doesn't work?
Second half.
One work and the other did not work or do not work.
So here's the thing. The order doesn't matter here. I just want one that works and one that doesn't work. So this can be done. So this, look, probability one works and one doesn't. Okay. Well, the way you can do that is you got to find the probability the first works and the second doesn't. Is there another way you can get one working one and one that doesn't work? Or what's the other way you can get one? You can use the complement. I'll show you the answer, and I'll show you another way to do it in a second. So look, I want one that works and one that doesn't work. So one way you can do this is the first work and the second doesn't, or the first one you select doesn't work and the second does. Do you see? All I said was I want one that works and one that doesn't work. I didn't specify the direct order. So you had to find the probability the first works and the second doesn't. The other way you could do it, or the first doesn't work and the second does work. In both those cases, you have one PlayStation that works and one PlayStation that doesn't. Okay. So look, you see the or statement. What does the or statement imply? What mathematical operator? Yep. So it's probably the first works and the second doesn't. Plus probably the first doesn't work. And the second works. So a lot of people in the chat initially did this first one. Probably the first one works is 16 out of 20 times probably the second one doesn't work. Well, there's 4 non-working ones and then only 19 PlayStations left. And then you need to add to it. Probably the first one doesn't work, which would be 4 out of 20. And then probably the second one works. Well, there's 16 working ones, but only 19 PlayStations left to pick from. So I believe 4 times 16 gets you 64. So this is 64 over 380 plus 64 over 380, which gets you 128 over 380. Which gets you like 34% roughly. Which is what you get. Someone mentioned the complement rule. You could do the complement of one works and one doesn't. Well, the complement is either the opposite of they both don't work or they both do work. And if you were to add 0.63 plus 0.03, you get 0.66, and then 1 minus 0.66 is this. So that's another way you could have done it. So when you see me write it like this, for those that initially got it wrong, does it make sense why I had to do it this way, or is it still like, what the heck, Matt?
Do you just assume you're not replacing it because it doesn't say without replacing? Is it because it's gonna? Oh, okay.
You randomly select two. I think yeah, because if you think about the context of the problem, like you wouldn't test the same one, right?
Yeah. Okay.
That's why. But like on the question on your exam, I think is a little bit
It'll
more
say- okay.
intuitive. So like a problem like I just did when you go to do your homework, question number 6 is just like this PlayStation stuff I did. Okay, especially when you get to this last one. One blue and one green. There's 2 ways you could do it. You could get a blue and then a green, or you can get a green and then a blue. All right. Is you guys okay if we get away from probability and do some counting stuff now? Just to get something different before class ends? The capitalized yes, get away. All right. Counting methods. I want to just get through, there's going to be a bunch of different formulas and methods in this class. I just want to get through the first one today, and then we'll finish this during the first part of class next time. And so when I say counting methods, this is going to be complex ways to count the number of ways, different ways you can select objects, or the number of different ways you can arrange objects. And it's not like counting like 1, 2, 3, 4, 5, 6, things like that. Like these are very difficult concepts. Or maybe not difficult, more interesting. So we're going to have all these rules for counting. So this is going to be the first one, the most important one. Rule number 1. And it's called the fundamental counting rule. Okay. And what I want to do is we're going to have an example with this, okay? And what we want to do in this example is we want to count the number of, yeah, Julia, so what happened was I didn't put up a slide for this today. That was my fault. I'm really, really sorry. It just, failure of me as a professor. So these are just slides that I put up for myself. But I'll put up the slides for Thursday so that they're there. Again, I'm really sorry about that. Let me just make sure I put that on a note. So tomorrow, as I said, I'm going to post a practice exam and I'll post the slides for Thursday. Okay, so we're going to set this up with an example of why we need this. So what I want to do is I want to count the number of unique work outfits Matt has. Okay. So I'm going to turn on my camera just for a second. Okay, nobody else has to do that. Can you guys all see me okay here? Guys see me okay here? Let's see. Okay. So when we're on campus, I actually dress very, very nicely for work, but on work days I have to I have to choose a work outfit that I have to wear to work every day. And so coming to work is going into my office. So you guys don't get to see me every day, but I wear the same outfit, okay? And so one thing I wear every day, does everybody see this? I wear a hoodie every day. Does anybody else wear hoodies? I wear a hoodie every day, okay? I put on a graphic t-shirt or a t-shirt of some type every day. And then I select a pair of jeans every day, okay? So I put on a hoodie, a t-shirt, and a pair of jeans, okay? I just thought I'd show the camera so you got a little little visual here. Yes, it is a fashion show. Not much of a fashion show though, Melissa. Okay. So let me give you, I'm just going to give you some information here, okay? So Matt has, I literally have about 15 hoodies. Okay. When I'm not at work, well, this is my work now. During the winter, I just like every day is a different hoodie. Okay. Today I'm wearing my Ocean Grove, New Jersey hoodie. Okay. I have about 20 different t-shirts. And then I have about 6 pairs of jeans. Okay. So the question is this: how many unique outfits does Matt have? Okay. So my question for you is this: when I said in this class, you wanted to count things, I generally said there tended to be a what type of effect or what type of mathematical operator would you use? Yeah. Okay. So this is really exactly what Julia has in the chat there. These counting methods are going to involve a lot of multiplication. Okay. So to answer this question here, this fundamental counting rule, we're going to have to be multiplying some numbers here. So is everybody okay if I go to the next slide to give you the definition, and then I'll come back to this slide? Okay. So this is the definition of the fundamental counting rule. So it goes like this: if a sequence of n events, and not if, I'm sorry, so for a sequence. So for a sequence of n events. And what I mean by a sequence, and I'm going to go back a slide for a second. My sequence is getting dressed for work every day, okay? And my sequence consists of 3 events, okay? That's what I mean by the n events. It consists of 3 things. I need to select my hoodie, I need to select my t-shirt, and then I need to select my pair of jeans. And that's it. That's my sequence, okay? In which the first event has k sub 1 possibilities. The second event has k sub 2 possibilities. And so on. So the third event has k sub 3, whatever. So how many ever. The total number of possibilities to the sequence will be, it's just k K1 times K2 times K3 times all the way to the last Kn. Okay. That's it. So if I wanted to figure out the total number of work, I'm going to put that in quotations, work outfits that I have nowadays. Okay. Here's what I would do. You would take the 15 hoodies times the 20 t-shirts times 6. And you said that was 1,800, Julia?
Yeah.
Yep. 15 times 20. Gosh, I have a lot of unique work outfits. Okay, I never need to buy clothes again. All right. So it's actually really a straightforward process there. You just got to realize, like going back, like, you know, do I have this sequence of n events that I need to do? And like, what are the number selections, things like that. Okay, but just remember, whenever you want to count something, it tends to be a multiplying effect. All right, you want to see some more? How about we got about 15 minutes of class left or so. Let me get a couple more examples in. Does that sound okay? And then we'll call it for today. Okay. Everybody okay if I go on now? Okay. Okay, so here's an example. There's actually kind of a funny story behind this, okay? One of the first vacations I ever took with my wife, she was my girlfriend then, was we went to Mexico, we went to Cancun, we went to one of those all-inclusive resorts. Has anyone ever, I'm just curious, has anyone ever traveled down to Cancun?
That is why I cannot drink tequila.
Well, it was a very nice trip. It was a lot of fun at the time. But here's the problem. So we woke up one morning and we were about to go on an excursion, and we went into my safe in the hotel room, and I looked in my wallet and I could not find my ATM card. This is a true story, okay? I could not find my ATM card. And I freaked out. I was like, oh my gosh, someone's gonna take my ATM card and they're gonna steal all my money. And my wife, my girlfriend at the time, was like, relax, Matt, you don't even have that much money anyways, it doesn't matter. Kind of funny. She didn't say that, but I like to say that joke. So I was a math, I'm a math teacher, so I was like, okay, if someone even got my debit card, right, what's the probability they could even guess my ATM, my PIN number? Okay. So Matt has a 6-digit PIN on my ATM. Okay. This is true. I have a 6-digit PIN on my ATM card. Okay. With a single guess, I know I said we're getting away from probability, but I'm going to ask a probability question that involves counting. What's the probability someone can guess his PIN? Okay. So I have a 6-digit PIN. So let me give you the rules of my PIN. Repeats are allowed. Yes, that's going to be the answer, Melissa, but I want to get there in a second. Any digit 0 to 9 is allowed. Okay. So I want to find the probability that someone takes my ATM card, okay, plugs it into the ATM machine and presses 6 random digits. Like this would be an acceptable PIN number. 137748. Okay. That's not my PIN number, by the way, but okay. So what's the probability they guess correctly? Okay. So to figure this out, we're just going to use some basic definition of probability. Okay. And then you'll see where the counting comes in. So the first thing, what goes in the numerator is the number of ways to guess correctly with one guess, because that's all you're getting. And I would have to divide this by the total number of possible what? Yeah, the total number of possible combinations. And what you mean there is the total possible number of PIN numbers there are. Okay, so I have to divide this by the total number of possible pins. So the numerator is easy, okay? If you get a single guess, okay, how many ways can you be correct with one guess? One way, that's it, just one way, yeah. That you plug this number into the bank machine and it is the correct number. So there's only one way you can guess correctly, okay? Again, that's not my PIN number, okay? So what you have to now figure out is the total number of pins. And to do this, you're actually going to use this fundamental counting rule, okay? So my PIN is a sequence of numbers, okay? So it's a sequence of n events, okay? So here's 1, 2, 3, 4, 5, 6 numbers you have to pick, okay? Well, if you want to figure out the number of ways this sequence can be constructed, you just have to take the number of possibilities for the first event times by the second event and so on. So for my first digit of my PIN, or how many possible digits could I choose from when I went to go pick it? For the first digit. Yeah, it's the digits 0 to 9. Okay, so that's 10 digits. If repeats are allowed, how many possibilities are there for the second digit? Yep, and so on for the third digit, for the fourth digit. The sixth, there's no 6. Oh, where did you get 6? Oh, I'm just telling you I have a 6-digit PIN, Jamie. Yeah, I was giving you that. So this is 1 divided by 10 times 10 times 10 times 10 times 10 times 10 is 1 million. So the probability that someone would have gotten my ATM card and stuck it in the ATM machine and guessed my PIN correctly would have been 1 in a million. Okay, so do you think I felt better knowing that was the probability? Actually, I felt even worse. It was like, oh, just my luck. They're going to guess. But just to put everyone's minds at ease, because I know you were all curious, I actually, the ATM card just fell like, it just fell out of my wallet and like under a mat inside the safe. Like they had a little like mat. So when I went home, when we got back from our excursion later that day, I just looked a little bit deeper in the safe and there was my ATM card. So it was safe the entire time. But that was a true story. If repeats weren't allowed, yes, it would be done like that. Yeah. Yeah. We'll talk about that's going to be something called a permutation later on, Melissa. And when we get to that, then yeah, you'll see. You're welcome. All right, let me just do one last one, and then we'll call it for today, okay? All right, so this is about stock names, okay? So there's a stock index called the Nasdaq. So stocks listed on the Nasdaq, all right, have names of either 2, 3, or 4 letters. Okay. So for example, the company FB is listed on there. Does anybody know? I'm just curious. I think it's Q actually, Nasdaq with the Q. Does anybody have a guess what the company with the stock symbol FB is? Yep, that's Facebook. How about, does anybody have a guess what this company is? TSLA. Yep, Tesla. And so on. Okay. I think Google before they became Alphabet was GOOG. Anyways, so companies listed on this NASDAQ, their company name has to either be two letters like Facebook here, 3 letters, or 4 letters. Okay, just some other rules. Repeats are allowed. Okay, so theoretically, there could be a company named ZZZZ. Okay, there could be, or AAAA, whatever. Okay, repeats are allowed. So my question for you is this, and this will be our last question for today. How many total stocks could be listed on this NASDAQ? So we have to figure out how many total stocks could be listed on this exchange. All right, I have no idea how to do this problem. Okay, that's not true. I know how to do this problem, but does anybody have a guess how to even start this? Okay. So the first thing you need to decide here is the stock could have 2 letters, 3 letters, or 4 letters. Okay, so you need to figure out the total number of 2-letter company names. And then if I want the total number, I would then need to add to it the total number of 3-letter names. And then I would need to figure out and add to that the total number of 4-letter names. You're close, Melissa. I like your thinking, but that's not exactly, you're off a little bit, but I understand what you're thinking. But it's not exactly like that. Okay, so first off, how many letters are there total in the English alphabet? Melissa has it there in the chat. Okay, there's 26 total letters. Okay. So if you're going to select a 2-letter name, going back. Look, this is a sequence of 2 events. Yeah, Barry has it. Thank you, Barry. Yeah, perfect. Awesome job. So the ways you could select the first letter is 26. And then when you go to select the second letter, because repeats are allowed, there's another 26. And then it's the same deal as Barry has in the chat there for the 3 letters. 26 for the first letter, 26 for the second letter, and 26 for the third letter. And then finally, for the 4th, 4-letter names, it would be 26 times 26 times 26 times 26. And then you could just, at this point, you could just grab your trusty calculator. Come on. 26 squared plus 26 cubed plus 26 to the 4th power. And it looks like there can be total number of stocks that can be listed on the stock exchange are 475,228. It's a lot. And there's nowhere near that many. So we're not running out of stock names just yet. We're all good. Okay, class. I know there was a lot of topics today. We're going to pick up exactly here next time. I'll post some new slides and a practice exam for you next class. And the recording for this will be posted in about half an hour. Okay. I'm not going to send out a email letting you know that the recording's done, but it's, yeah. Give me one sec. Where do you need me to go back to, Jamie?
The last slide we were just on.
Yep. Give it 1 second, Mike. It's just saving. This one right here.
The one with the names.
This
Oh,
right
yes.
here.
Thank you.
Yeah. No problem. So I'm not
Professor?
going to, oh, go on ahead.
I'm sorry, you said for tonight we should be able to do 5 and 6, correct?
Yeah. So on the homework, you should be able to do at this point. Questions 1, 2, 3, 4, 5, 6. You could actually do question 11 too.
Thank you.
1 through 6, and you could do question 11. Oh my gosh, question 11 I just did in class for you. Ha! So that one should be easy. Ha! To stop the recording,